We're group 7, and we decided to do Newton's law of cooling. Newton's law of cooling states that the rate at which an object loses heat is directly proportional to the temperature of the object minus the temperature of its surroundings. This is the equation for Newton's law of cooling. In this equation, big T will represent the temperature of the function, little t will represent time. T sub A will represent the ambient temperature, aka the temperature of the surroundings. T naught will represent the initial temperature of the object, and K will be the proportionality constant in this equation.
So, in the Newton's law of cooling equation, the only variable unaccounted for is the proportionality constant K. In solving for K, we would take the natural log of the temperature at a specific time minus the temperature of the surroundings divided by the initial temperature minus the temperature of the surroundings. This would all be over a specific time t, and K is negative because the object is cooling over time.
To conduct our experiment on Newton's law of cooling, we ran 2 separate trials with 2 250 milliliter Erlenmeyer flasks. One flask was filled with 150 milliliters of water and the other was filled with 200 milliliters of water.
That's good.
The flasks were sealed with rubber stoppers to ensure the water was enclosed and wasn't affected by air seeping into the flask. To record the temperature of the water, thermocouples connected to the LabQuest provided in the laboratory kept track of the temperature of the water inside the flask by placing the thermocouples through the rubber stoppers and into the water. To start off, the air temperature or ambient temperature was recorded to be 73 degrees Fahrenheit. Both of our trials were heated to 162 degrees Fahrenheit, our initial temperature, before being left to sit for an hour. Over this hour time span, the temperature of the water in each flask was recorded at every 5-minute interval, either manually or automatically using the lab.
After testing the Newton's law of cooling in the lab, we plotted our data into Excel and came up with these 2 line graphs you see here. The top graph is the results from 150 milliliters, and the bottom is for 200 milliliters. Time is plotted across the x-axis and the temperature is plotted along the y-axis. On the right, you can see the average K calculated from both tests. We can see the exponential curve on both of the graphs come to a constant as the water in the flask cools to a certain constant temperature. Both show the temperature falling quickly then slowly decreasing over time, thus proving Newton's law of cooling.
Some of the errors we encountered while experimenting were the accuracy of our ambient temperature reading, holding the ambient temperature to a constant, the effect of the glass flask on the cooling rate of the water, and the mean error in calculating our K value.
To apply Newton's law of cooling to real-world applications, we can look at the world of forensics. Forensic scientists use Newton's law of cooling to determine the time of death of someone who has recently died. Another common use is in water heaters. Every household in all public places will have a water heater, either in an attic like mine is here, or in a basement. It applies to Newton's law of cooling to show how fast the heater cools when it is turned off, like for instance when people turn it off when they leave for a vacation.
You're as cold as ice. You're willing to say